Okay, in this video we'll take a look at how to find the limits of rational functions. And just a reminder, what a rational function is, it's one polynomial over another polynomial. So when you find these limits, there's really three possibilities. And they're all displayed on this graph right here. So we'll look at possibility as you approach A, as you approach B, and as you approach C. Now the first possibility is this. We'll find the limit of f of x as x approaches A. So as the limit as x approaches a, in this case, this is a point where the function is continuous. If the function is continuous, then the limit is just whatever the value of the function is at that point. So what this means, the limit of f of x as x approaches a, means that as x approaches a from the left and from the right, if you come straight up from there, the question now is, what is y approaching? So as x approaches a, then the limit would be, what is y approaching as you come at it from both directions. Now, if you come straight across horizontally here, you will see y is approaching, we'll go over to here, 2. So on this first example, the limit of f of x as x approaches a would be 2. So as x approaches a, the function itself, y, is approaching 2. Now what that is, that's where it's continuous. Now in the second example, we'll take a look and see what it looks like if you happen to have a hole in it. Now some graphs have a hole in them, and we'll describe where that hole comes from later on. But suppose you had a graph with a hole in it. What happens if you take the limit of a rational function at a point where there's a hole in the graph? Now you use the same definition, so we'll find the limit of this function as x approaches b. So what will happen as x approaches b from the left and from the right, then the question is, what is the function approaching? So go straight up from that point until you hit the function, then put your fingers on the function and approach it from the left and approach it from the right, and ask the question, what single fixed number are your two fingers approaching? Well, in this case, they are approaching 5. So in this case, the limit exists, and it is 5. So the limit of f of x as x approaches b would be 5. So in this case, the limit exists. In this case, if you have a hole, the limit exists. So if the function is continuous, or if you have a hole, the limit exists. Now the third possibility, suppose you have an asymptote. So if you came on to this thing, you've got an asymptote where the function is not defined. So now the question is, what is the limit of this function as x approaches c? We'll do exactly the same thing. Approach c from the left and from the right. Now put your fingers on the graph and so watch out. This one is going down, and actually it's going down toward a negative infinity. This one is also going down toward a negative infinity. Now in this case, the function is not settling on a single fixed number, so you would have to conclude that in this case the limit does not exist. So the limit at an asymptote does not exist. Now in this video we'll use this. We'll put D in E for does not exist. Anyway, just remember, if it's continuous, it exists. If it's got a hole, the limit exists. But if you have an asymptote, at that point the limit does not exist because the function is not defined at that point, and the limit is not settling in on a single fixed number. So that's our just opening discussion on the three possibilities that we're going to be looking at. Okay, let's take a look at the first example, and what the first example is going to be. This is actually just the limit of a polynomial. So if I were to find the limit of this number, whenever you're working with polynomials, polynomials are continuous lines. So the limit will be the same thing as the value of the function at that point. So whenever you're working with a polynomial, all you have to do is just plug the number that you're interested in into the function. So what this thing says is as x is approaching 3, it looks like this. So as x approaches 3 from the left and from the right, you can just take this 3 and plug it into the function. So you get 3 plus 2, which would be equal to 5, and that is the limit. Now graphically what that means is this. As x approaches 3, go straight up from here until you hit the function. Now you put your fingers on the function, approach it from the left and from the right, and what is the function approaching? Well, the function is approaching 5, and that is your limit. So this is what it looks like algebraically, and this is what it looks like graphically if you did it. So whenever you're working with a polynomial, you can just plug the number into the polynomial, and you'll have your answer. Okay, now what we've got is this. We want to find the limit of this function as x approaches 3. Now, first of all, look at the graph of this function, and let's go back to the previous function. You'll see they're exactly the same graphs. This one is exactly the same one as this one. So this is the graph of x plus 2, just a straight line, and we're going to compare that to this one. Now, they have exactly the same graph except for this hole. Now, let's look where the hole comes from. Now, whenever you're working with a function like this, the very first thing to do is to try to just plug the number in. If you're lucky, if you plug it in, it'll work, but watch what happens here. If you put a 3 into the denominator, then you get 3 minus 3, which is 0. So you've got a problem at x equals 3. But you're trying to find the limit here as x approaches 3. So as x approaches 3, now if you look at it, you can tell that the answer, it's actually going to have an answer. This thing is going to approach something, and it's going to approach this. But the question is, what is it approaching here? So what is this limit? Now, if you've got a problem like this, try to plug the number in first. If you can't plug it in, then your next step is to factor it and see if you can cancel something out. So let's try that. This would be the limit as x approaches 3. And go ahead and factor this top thing. So this will factor into, this would be an x minus 3. Oops, x minus 3 times an x plus 2. And it's going to be divided by, in the bottom you've got an x minus 3. Now what you'll find is this. You've got an x minus 3 in the top, you've got an x minus 3 in the bottom. These will cancel out. So this one will cancel out this one. And if they cancel out, what you'll find is that is where you have a hole. So if you can cancel it out, you have a hole. So now you do the following. Since those cancel out, that leaves you with this equivalent problem. What's the limit as x approaches 3? And the only thing that's left over now is x plus 2. So what you did in this case, you canceled out the problem, and it reduces down to this. Now again, this, and we'll go back to that first example, is exactly the same thing as what this first example is, but without the hole. So if we go back to our original problem now that you've canceled out the problem, you can go ahead and plug in it. So take this 3 and try to plug it in right here. So I've got 3 plus 2, the limit is 5, and that is your limit. So this would be 5 right here. So the limit of this thing is this. So where the hole comes from, once you've got a hole, to figure out where it is, set the denominator equal to 0. So I've got x minus 3 is equal to 0. So I have a hole at x equals 3. So you know you have a hole where x is equal to 3. So again, if you can factor it out, it's a hole. If you can't factor it out, you'll see later on, it'll be an asymptote. Okay, now in the next problem, let's do this. Let's look at exactly the same problem, but rather than trying to find the limit as x approaches 3, let's find the limit as x approaches 1. Now in this problem, your first step is always to try to plug the number in and see if it worked. When you tried to plug in the 3, you had 3 minus 3, which is 0. You had a problem, so you had to try to factor it out. But occasionally, if you're lucky, you can just plug in the 1 and off you go. So let's look at exactly the same problem, but this time as x approaches 1. Now, if you do this, here's what you'll have. You've got exactly the same thing. You've still got that hole at 3, but always try to plug in the number first. If in a rational function, if you can plug in the number and it works, then great, you're good to go and you don't have to do anything else. So what we'll have, we'll make this is going to be the limit of as x approaches 1, and actually just go ahead and plug in a 1 to this entire thing. So this would be equal to, I'll plug in a 1 here. So everywhere you've got an x, plug in a 1. So minus 1 minus 6 divided by 1 minus 3. Now what that'll give you is 1 minus 1 would cancel out, and that's going to give you a negative 6 over a negative 2, which would be equal to 3. So that's going to be the limit. Now graphically what that looks like would be this. Here is 1, and you want to find the limit as x approaches 1. So you come at it from here and here, go straight up from here, and straight across from here, and you will get 3. So as x approaches 1, this graph is approaching 3. So on all problems, try to plug in the number first. If you're lucky, you don't have to factor anything. It just works. If you have a problem with the denominator, that's where you have to try to factor something out and see if you can cancel something. Okay, now just a reminder, the first step will always be, whenever you're working with rational functions, if you're lucky, just plug in the number, and if there's not a problem in the denominator, you'll get a limit and you're done. So that'll be the first step. But remember, on some of the problems, let's go back to the previous problem, if you try to plug in the 3, you had a problem in the denominator. So you factored it, and then you were able to cancel it out and continue on to find the limit. So just remember, if you can cancel it out, if you factor it, then you can cancel it out, it's a whole. If you factor it, but you can't cancel it out, it will turn out to be an asymptote. And you can actually write those as rules that will look like this. So these are actually going to be the rules that we'll follow. Okay, first of all, try to plug the number in. If it works, great, you're done. Secondly, if you try to plug the number in and you've got a problem in the denominator, then try to factor it. Now, after you factor it, you've only got 2 possibilities. If you can cancel the factors out, then you know that you have a hole there and the limit exists. If you can't cancel the factors out, then you know you have an asymptote and the limit does not exist. So it's got to be one of those 2 possibilities, and really only one of those 2 possibilities. So with that in mind, let's take a look at another example. Okay, now what I've got is this. I want to find the limit of this function as x approaches 3. So let's start across, and we'll try it first of all by just plugging something in. If you try to plug the 3 in, you've got 3 minus 3, you've got a problem, so you've got to try to factor out that problem. So this will become the limit as x approaches 3 of, and go ahead and factor the top thing. So this will factor into an x plus 3 times an x minus 2. So an x plus 3 times an x minus 2. Now in the denominator, you've got an x minus 3. Now again, just a reminder, let's go back to that one of our previous examples. In a previous example, we had this. You had an x minus 3 on the top, you had an x minus 3 on the bottom. They canceled out, so you knew that that was a whole and you could continue on. But look at this problem. You've got an x plus 3 on the top, you've got an x minus 3 on the bottom, so nothing cancels out. And what that tells you is, since you can't factor out this factor in the bottom, you know that that is an asymptote. So you've got an asymptote at, and then set x minus 3 equal to 0, you've got an asymptote at x equals 3. Now, in this case, what happens is this, is you tried to factor out the problem, but you can't cancel it out, so you've still got a problem. You can't plug the 3 in. You know it's an asymptote, so in this case, you would have to conclude that the limit does not exist. So if you can't cancel out the problem, the limit does not exist. Now, this will make a lot more sense if you see it, what the graph looks like. So let's take a quick look at the graph. So what the graph of this would look like is this. You've got an asymptote right here at x equals 3. So there is the asymptote. Now again, if you do your limit thing, you want to find the limit as x approaches 3. So as x approaches 3 from the left or right, now this part of the function is going down toward a negative infinity. This part of the function is going up toward a positive infinity. They're not settling on a single fixed number, so the limit does not exist at as x approaches 3. Okay, now in some problems, you can have both wholes and asymptotes, so let's take a look at that. Now first of all, let's try this. Always try to plug the number in first. If you try to plug in the 2, you'd get 4 minus 4, you'd get 0, so you've got a problem in the denominator. So you have to try to factor and eliminate that problem. So find the limit as x approaches 2 of this function. Now, in this case, you're going to have to factor both the top and the bottom. So the top will factor into x plus 4 times an x minus 2. the bottom, that's a perfect square. That'll factor into an x plus 2 times an x minus 2. Now right away you know the following things. You've got two possibilities. The x minus 2 in the top will cancel out the x minus 2 in the bottom. So this one cancels out this one. Now if you can cancel them out, you know that this thing, you have a whole at, and set this equal to 0. So x minus 2 is equal to 0, x is equal to 2. So you have a whole at x is equal to 2. Now on this one, you can't factor that, you can't cancel that one out, so it tells you that you have an asymptote here. So you have an asymptote at, and again, set the x plus 2 is equal to 0, so x is equal to a negative 2. So you've got an asymptote at x is equal to negative 2. So you can tell whether you have a whole or an asymptote. Now again, this one canceled out, so once you've canceled something out, go ahead and continue on and see if you can find the limit. So now you want to find the limit as x approaches 2 of what's left over. So you're going to have an x plus 4 in the top and an x plus 2 in the bottom. Now at this point, now you can plug in that 2. Plug a 2 into the top and you'd have 2 plus 4. Plug a 2 into the bottom, 2 plus 2, and you're going to wind up with 6/4 or 3/2. So the limit of this thing is going to turn out to be 3/2. So algebraically, that's how you do it. You got both a whole and an asymptote. Now again, let's look at the graph to see why it makes sense. If you did the graph looks like this. What you got, if you graphed it on a graphing calculator, you would see this. At 2, you've got a whole right here. At negative 2, you've got an asymptote over here. Now you want to find the limit as x approaches 2. So graphically what you're doing, you're approaching 2 from the left and from the right. If you go straight up from here, there's the limit. Now the question is, what is the function approaching as it comes this way and this way? And it is approaching, if you came over to here, 3/2. So y would be equal to 3/2. So that's going to be the limit. So as x approaches 2, this approaches 3/2. So you have a whole, but the limit still exists. Okay, let's take a look at this next problem. Now first of all, in the last problem, what you had a whole and an asymptote in the same problem, and the limit existed. In this problem, you'll have a whole and an asymptote, but the limit will not exist. So let's take a look at what this is going to look like. Okay, again, your first step is always take the 3, try to plug it in. If you're lucky, it'll work. But the trouble is, you'll get 9 minus 9. You've got a problem, so you've got to try to factor out that problem. So we'll go ahead and factor it. This will become the limit as x approaches 3 of the following. Now, factor the top and factor the bottom. This will factor into an x minus 4 times an x plus 3. And the bottom will factor into an x plus 3 times an x minus 3. Now, what that's going to give you, initially, again, cancel out what you can. Now, you've got an x plus 3 in the top and x plus 3 in the bottom, so this one will cancel out this one. And what that tells you is that this thing right here is a whole. So you have a whole at, and set the x plus 3 equal to 0. You get x is equal to a negative 3. So you've got a whole at x equals negative 3. So you know you have a whole right there. Now, this one did not factor out, so you know that this one is an asymptote. So you've got an asymptote at x equals what? So set the x minus 3 equal to 0, which gives you x is equal to 3. So you've got an asymptote at x equals 3. So in this problem, you've got both a whole and an asymptote. So now continue on and rewrite it. That's going to give you the limit as x approaches 3. Now the x plus 3's cancel out, so all that's left over is an x minus 4 divided by an x minus 3. But the problem is this: if you try to plug in that 3, even though you factored it and canceled out what you can, you still got a problem at 3. If you try to plug that in, it's undefined. There's nothing you can do to get rid of the problem, so you have no choice but to conclude that the limit does not exist. So in this case, the limit doesn't exist. Again, let's take a look at it graphically and see what that's going to look like. So if you look at the graph, here's what it would look like. You've got a hole at -3 right here. You've got an asymptote at +3 right here. Now your question was, what's the limit as x approaches 3? So again, as x approaches 3 from the left and from the right, the function, this one's going up toward a positive infinity, and this one's going down toward a negative infinity. They're not settling on a single fixed number, so again, you'll conclude that the limit does not exist. So that's what it looks like algebraically, and this is what it would look like graphically. Okay, now in our next problem, let's do the same thing. Let's work exactly the same problem, but rather than having x approach a +3 over here where the limit does not exist, let's suppose we did the following. Let's take exactly the same problem and let x approach a -3. So I'll let x approach a -3 here. And here's what the thing would look like. Okay, we're going to let exactly the same problem. X is going to approach a -3. The graph will look exactly the same, but rather than approaching -3 or +3, we'll approach a -3. Now our approach will still be exactly the same thing. First of all, try to plug in the number and see if it works. If you try to plug in the -3, then you get 9 minus 9, you get 0. So you're going to do exactly the same thing algebraic that you did last time. Find the limit as x approaches a -3, and again, factor this thing just like you did before. That'll factor into an x minus 4 times an x plus 3. The bottom will factor into an x plus 3 times an x minus 3. And then again, cancel out what you can. So you can cancel this out and you can cancel this out. Remember, you can cancel it out, so that's a whole at x equals -3, just like you had last time. This one you can't cancel out, so you would have an asymptote at x equals, and then set that equal to 0, you'd have a +3. So you'll have a hole and an asymptote, so that part's exactly like before. Now this time though, when you try to plug in, watch what happens. Last time you had that the limit did not exist. So now you're going to want to find the limit as x approaches a -3 of x minus 4 divided by x minus 3. But now you can plug in the numbers. If you plug it in, you will not get division by 0. So this will become a -3 minus 4 divided by a -3 minus 3. And that'll turn into a -7 over a -6, which will turn into a +7/6. So in this case, the limit exists, and it's 7/6. Now graphically, what that would look like would be this. As x approaches -3 from the left and from the right, if you go straight up from here, you've got a hole, and you knew you had a hole because there it was right there at x equals -3. But this time, if you find the limit, if you go straight across here, that occurs at when y is equal to 7/6, and that's going to be your limit. So that's an example of a problem. Depending on where you take the limit at, maybe it exists, maybe it doesn't exist. Just depends on the problem. Okay, let's take a look at one last problem, and mainly just because this one has a little algebra trick in it. Now, first of all, let's run through this. Do like all the other problems, try to plug in a 3 and see if it works. If you plug it in, you get 9 minus 9, doesn't work, so you got a problem. Try to factor out the problem. So what we'll do is make this be the limit as x approaches 3 of, and then in the numerator, you've got 3 minus x. In the denominator, you can factor that into an x plus 3 times an x minus 3. Now here's something that causes students a lot of trouble. You go, well, I've got a x minus 3 in the bottom. What I need is an x minus 3 in the top to cancel it out. At first, it looks like you can't cancel anything out. But just remember, there's a little algebra trick. You can switch these two. If you were to take these two and switch them, then that will factor into this. This will make it become the limit as x approaches 3. Now when you switch them, you can factor out a -1. That's like having a -1 times x minus 3. So whenever if you have a 3 minus x, but you need an x minus 3, switch them, factor out a -1. So that's going to give you an x plus 3 here, and an x minus 3 here. Well, now you can cancel things out. So this one will cancel out this one, which tells you that you have got a whole at, now again set the x minus 3 equal to 0, that gives you x is equal to 3. So you've got a whole at x is equal to 3. So you know that. Now this other one you can't factor out, so what this one's going to give you, this one's going to be an asymptote. So you're going to have an asymptote where you can't factor it out. At x equals, and again set the x plus 3 equal to 0, which gives you x is equal to a -3. So you've got an asymptote at x equals -3. So in this problem you've got both a whole and an asymptote. Well, now continue on. What that's going to give you would be the limit as x approaches 3 of -1 over x plus 3. Now you can plug in a 3. If you plugged it in, you would have -1 over 3 plus 3 would be 6. And that's going to be your limit. So your limit will actually exist, and it'll be a -1/6. Again, let's take a quick look at the graph, see what the graph looks like. If you graphed it, it would look like something like this. We're going to go over here to -3. So I've got a -3 right here. And I've got an asymptote that would look something like this. So it goes kind of like this right here. Now, if you graph this thing on a graphing calculator and did the graph, it would look something along this line. It comes in something like this, and it would go up like that. Then it comes in from the bottom here, and it would go something kind of like this right here. Until you got to 3, and when you get to x equals 3 right here, you would have a hole in the graph right there. And then the graph goes on like that. Now again, what you're asking for, you want to find the limit as x is equal to 3. So as x approaches 3, this thing is approaching right here, and if you go across to here, you would have -1/6. So as x approaches 3, y approaches -1/6, and that's what it looks like. But again, I think I'll go back to the rules one last time. Really, it comes down to this. First of all, try to plug in the number. If you can plug in the number, great, you're done. If you try to plug in the number and you got a problem in the denominator, then try to factor it. After you get it factored, if you can cancel the factor out, it's a whole, and the limit exists. If you can't cancel it out, it's an asymptote, and the limit does not exist. And really, those are the only things you need for finding the limits of rational functions.